Our first speaker is John Perdew from Tulane University, who will tell us about predictive power of the exact constraints in density functional theory, new evidence from 3D atoms.
Yeah, so I spent most of my career at Tulane University. I spent 10 years at Temple in Philadelphia, and now I'm back at Tulane again. I probably have a distinction that no one else in this room has, except, of course, Allan himself. And that is to have been a co-author of Allan's first paper. So I'm going to show you that paper. Oops, I threw it too fast. So he had a good start. It was a physical review letter. This is 1975. It's coming from the Department of Physics in Arundel College at the University of Toronto, where I was a postdoc and Allan was a graduate student, and we were both in Cy Vosko's group. The paper is about density functional theory. It's a calculation of the spin susceptibilities of the alkali metals using the density functional theory with the local spin density approximation, which was the only functional available in those days. And you can see the conclusion, the excellent agreement between the results and recent experiments establishes the validity of this new theory and the correctness of the theoretical values for the exchange correlation enhancement of chi, the spin susceptibility for a uniform electron gas at valence electron densities Rs less than 6. This was not my first paper, and it wasn't even my first paper in density functional theory, but it was my second paper in density functional theory, because when I was a postdoc with Cy Vosko in Toronto, we were using the Hartree approximation to calculate electron-photon interactions. It wasn't very good because the phonon frequencies were way too low, but it was the best that we knew about. And Mark Rassault, who had been a postdoc at National Research Council in Ottawa, moved to Toronto to begin as a second postdoc with Cy Vosko. And Mark brought the news to us that there's this new theory, relatively new at that time, that density functional theory that works and is much better than the Hartree approximation. So that's when I got interested in it. I've never stopped being interested in it. And there's still a lot to be done. Although the theory is very old now, there's still a lot more that can be done to improve it. Unfortunately, this was also my last paper with Allan. We did have a grant proposal together, which wasn't funded. So, well, there's always hope for the future, right? Okay. So let me go on to my talk. Cone-sham density functional theory is a simplification of the many electron quantum mechanics, which requires only the solution of self-consistent one electron equations. But of course, it's not a one electron theory, it's a many electron theory, and the interactions between the electrons are included fully for the ground state, at least in principle. So the theory is exact in principle for the total energy and electron density of the ground state of a many electron system in the presence of a static scalar external potential, which is a pretty good approximation to the problems we have to deal with. And for practical reasons, the density functional for the exchange correlation has to be, energy has to be approximated. So there are different ways to approximate this functional. Some of them involve very heavy fitting to experimental data. Others rely more on exact constraints. So because there is an exact exchange correlation energy functional, it's possible, and we can write down what it is in principle, even if we can't evaluate it on the computer, because it involves searching over correlated wave functions. But because we can write it down, we can derive exact properties of that functional, and many have been derived. Over 20 exact constraints have been derived since the 1970s. And there's still occasionally new ones are being derived, but it's slowed down. And in addition to you satisfying these exact constraints in the approximation, I believe it's fair game to use appropriate norms, which are non-bonded systems for which the functional can be very accurate. So the original appropriate norm was the uniform electron gas, where we know the exchange correlation energy very accurately now for each electron density. And atoms are also appropriate norms in the sense because the total energy of an atom can be calculated very accurately with modern density functionals. Okay. So we use in our work for appropriate norms, we use the uniform electron gas, and we use closed shell atoms, typically the total energies of rare gas atoms. And that means that any prediction that we make about bonding is a genuine prediction. It's not a fit to anything, any bonded system. So functionals that are constructed that way can usefully predict bonds in molecules and solids. We can predict the binding energy. We can predict the bond lengths, the crystal structures, and so on. The magnetic states in many cases. And in our work, the exchange correlation energy density at a point in space is constructed from local ingredients there. And typically, as you add more local ingredients, you can use them to either fit more data or satisfy more exact constraints, or both. So the earliest density functional comes from Cohn and Sham in 1965, and that's the local spin density approximation. It uses only one local ingredient. So the energy density at a position R in space is constructed from the electron spin densities, up and down electron spin densities at that point in space. And although it was only designed to be exact for an appropriate norm, the uniform electron gas, it actually inherits from that system the satisfaction of nine known exact constraints. That's why it works as well as it does. If it didn't inherit those constraints, it would not work so well. And at the next level of approximation, we construct the energy density at a point R in space from the local density at that point and the gradient of the local density at that point. These are called generalized gradient approximations. And the PBE generalized gradient approximation from 1996 was designed to satisfy 11 exact constraints. And it in fact works significantly better, and typically works significantly better than the local spin density approximation. And then on the third rung of this Jacob's ladder of approximations, we construct the energy density at a position R from the local density at that point, the gradient local density, and also the local orbital kinetic energy density, a positive orbital kinetic energy density that we can construct from the occupied Cohn-Sham orbitals. So in Cohn-Sham theory, we solve a self-consistent one electron problem that gives us orbitals, and that provides additional useful ingredient for constructing the functional. And from those three things, N, del N, and tau, we can construct a dimensionless variable called alpha, which is a function of which is a function of R. A function of it varies from one point to another in an inhomogeneous system. Alpha is a positive number which can identify qualitatively different regions of space. For instance, alpha can recognize regions of space where a single orbital shape dominates the density. We call those isoorbital regions. That includes all one electron regions. So it's quite easy to recognize one electron regions and give a special GGA description for one electron regions. It's possible to recognize slowly varying regions in space, like the uniform electron gas or an electron gas of slowly varying density, because those are regions where this dimensionless variable alpha is close to 1. And we can also recognize overlap tail electron density regions. So for instance, if you take two argon atoms and you push them together, the density tails start to overlap. And that happens roughly in the region where the van der Waals interaction is most important for the ground state properties. So we can even get van der Waals interactions from alpha. The functional that I'm going to be discussing today is called R2 scan. So R2 means revised and restored, or regulated and restored, I guess. Regulated and restored. And SCAN stands for strongly constrained and appropriately normed. That means that we use the constraints and the appropriate norms to construct it. The principal author of this SCAN work is Janwei Sun, who's now a faculty member at Tulane, where I am. And Adrian Rajinski, James Furness, Aaron Kaplan, and so on have also worked on R2 scan. R2 scan and scan are almost the same functional, but R2 scan is more computationally efficient because it smooths out the energy density in a useful way. So scan and R2 scan were designed to satisfy 17 of the about 20 known exact constraints, and also the appropriate norms that I mentioned before. But the most important exact constraint, in my view, has not yet been satisfied by any widely used density functional, even after almost 60 years of density functional theory. And that is a very simple and natural constraint that the approximation should be exact for all one electron densities. That's been very hard to satisfy in a useful way. You can satisfy it. I did work with Alex Unger in 1981, which takes any approximate functional and makes it exact for all one electron densities. But there are problems with that when you get into many electron regions that maybe I can discuss later. So anyway, we're working on that problem, trying to find a good self-interaction correction to R2 scan. Here are some of my group members: Chandra Shahi, Rohan Maniar, Allan Jackson, Juan Peralta. So I'm just going to do a very quick overview of some of the many systems for which scan has been successful. It's not successful for everything. What we want is to get a functional that's typically better than the generalized gradient approximations like PBE, and R2 scan is in fact that functional. But it's not true that in every property of every system is improved. It's a statistical thing, but overall there's a great improvement. And here are some of the successes of R2 scan. First of all, we get more accurate atomization energies and barrier heights for sp bonded molecules. Chemists care a lot about that. And it's much better with R2 scan than with PBE or LDA. We get a correct prediction of the so-called artificial molecules that Stefan Grimme designed. He does something very simple. He just takes a random selection of atoms, maybe 16 atoms, and he throws them in And he finds a bound state using wave function methods. And typically it's a stable state in the sense that if it would be stable if it were isolated, but in a real chemical environment, it's quite unstable because other molecules that are more strongly bound will come and eat it away. But this is still a good test set for density functionals because no density functional has ever been fitted to these artificial molecules. And on that test set, it turns out that SCAN does much better than the functionals that were fitted to standard molecules. R2 scan is more accurate for the geometries of molecules and solids. It predicts good geometries, it predicts good electron densities for these systems. It gives more correct structural predictions. It makes about half the structural prediction errors of PBE, and PBE is not bad for structures. You get more accurate phonon frequencies, a lot more accurate phonon frequencies. And interestingly, Janwei-san and Aaron Bansal and others have found that R2 scan and R2 scan give a nearly perfect description of the cuprate high temperature superconducting materials. Not the superconductivity itself, but all the properties of the material from which the superconductivity arises. And it even predicts the correct doping ratio at which the material goes from insulating to metallic and can become a superconductor. But what I'm going to talk to you about today is a much simpler system, 3D transition metal atoms. And for most of these atoms, for most of the solids that you can make for these atoms, let's say transition metal oxide solids, R2 scan does need a correction, like a Hubbard plus U correction, which is a kind of effective self-interaction correction, or can be thought about that way. There's a parameter U, which has to be either computed laboriously or fitted to experiment. And U turns out to be significant, to decrease significantly when we go up the density functional ladder from LSDA to PBE GGA to R2 scan meta GGA. Emily Carter and her collaborators have shown that. And this shows that when you satisfy more exact constraints, when a functional satisfies more exact constraints, that reduces its self-interaction error, but it doesn't eliminate it. We have not succeeded in eliminating the self-interaction error. So these 3D transition metal solids have many actual and potential applications that you know about, including catalysis. And a necessary but not sufficient condition for a density functional to be accurate for these 3D solids would be a correct description of the balance between competing S and D states in the system, and particularly in an atom, and an accurate description of the first three ionization energies of the 3D atoms, which are regarded as proxies for the oxidation states of the transition metal ions in the solid materials, in the oxides, for instance. So, so in an atom, there's no long-range charge transfer error for which a plus U correction could be needed. There's only one center, so there's no transfer of charge from one center to another, but there are still some self-interaction errors in the functional. So what I want to tell you about today is new work by Rohan Maniyar, Priyanka Shukla, Carl Johnson, Allan Jackson, and myself. It's on the archive. It's being revised now in response to reviewer comments. There are 10 3D atoms, starting at scandium in the periodic table and ending at zinc. And except for chromium and copper, all of the neutral 3D atoms have the electronic configuration 3D n-2 4s2. And interesting, there seems to be strong correlation in the atom for the 4s2 configurations. And that's due to a near degeneracy between 4s2 and 4p2. So you get two Slater determinants that are strongly mixed by this near degeneracy and by the matrix elements of the Coulomb interaction. The same thing is known to happen in the beryllium atom, where you have a 2s2 configuration that is nearly degenerate with a 2p2, and you also have strong correlation. So this, for the transition atoms, this was suggested by a quantum chemist, Buendia, in 2003, and he used fixed node diffusion Monte Carlo calculations, and he suggested that this strong correlation increases the first ionization energy of the neutral atom in the 4s2 configuration by about 0.8 of an electron volt. And our R2 scan calculations actually corroborate that. So it seems that there really is strong correlation in nearly all of the neutral atoms. So I'm going to jump I'm not going to tell you more about the first ionization energy because that's a little problematic. We have to get the strong correlation right to get that right. And we haven't done that yet, but maybe we can with symmetry breaking. We haven't really tried. But let's go on, jump ahead to the second and third ionization energies, and I'll show you how things are performing. Approximate density functions can sometimes at least describe strong correlation through symmetry breaking. That happens in many cases. It happens for stretched H2. It happens for the carbon-2 dimer in its ground state at the equilibrium bond length. There's strong correlation there. R2 scan can detect that strong correlation and it can actually fix it through symmetry breaking. So unexpectedly, in the 3D atoms and ions, atomic ions, it's the 4s and not the 3D electrons that are hardest to get right. And to avoid the problematic 4s2 configurations, we'll focus on the second and third ionization energies in this talk. And I'm going to report mean errors, mean percent errors, mean errors ME, the mean percent errors MPE, mean absolute errors MAE, and mean absolute percent errors MAPE. And they're in my table here. The first table is for the second ionization energies of the 10 3D atoms, which involve removing a D or an S electron with a roughly equal frequency. I'm showing you three approximate functionals: the local spin density approximation, the Perdew-Burke-Ernzerhof generalized gradient approximation, the R2 scan meta-generalized gradient approximation. So as you move down on this slide, you're climbing up on the Jacob's ladder of approximations. And notice that the errors are decreasing in a very regular way. So the mean absolute error is 1.1 electron volts for LSDA. That's unacceptably large. For PBE, it's still 0.7. For R2 scan, it's 0.3. It's not bad. And the relative errors are also decreasing from about 7% to about 2%. When we go to the third ionization energies of the 3D atoms, we're always removing a d electron. The first s electron or the first two d electrons have been removed, and we're now removing d electrons. And you see the same story. The error decreases nicely from, the mean absolute error decreases from 1.1 electron volts in LSDA to 0.8 in PBE to 0.4 in R2 scan. And the mean percent errors also decrease about the same way. That's the typical behavior. It's not the universal behavior, but it's a typical behavior of what happens when you go from, when you climb the ladder. Climb the ladder and climb the non-empirical ladder too, I should say. the ladder of non-empirical functionals. Another thing that improves when you climb up that ladder is the energy balance between the s electrons and the d electrons in the atom. And I measure that imbalance by this quantity I call delta SD. I call that the SD energy imbalance. So I look at second ionization energies of the 10 3D atoms. And I find the mean error for d electron removal minus the mean error for s electron removal. And you can see that that also decreases as you climb up the ladder from 7/10 of an EV for LSDA to 1/10 of an EV for RT scan. So we're getting a better balance of s and d electrons, and a better energy balance. So that's basically, I'm at the summary. I have this and one more slide and I'm done. So accurate and predictive, but computationally efficient density functionals can be constructed without fitting to any bonded system. All you have to do is satisfy more exact constraints and more appropriate norms. It works pretty reliably. It's worked pretty reliably over time, and I think it will continue to work for a while, at least. The second and third ionization energies of the 3D atoms and the SD energy imbalances improve systematically from LSDA to PBEGG to R2 scan meta GGA. The reason why the first ionization energies are a more complicated story is that the 4s2 configurations display a strong or abnormal correlation due to the near degeneracy between the 4s2 and the 4p2 configurations. And we don't know yet whether this can be fixed by coaxing out the appropriate symmetry breaking in R2 scan, but we're trying that. My student Rohan Maniar is working on that right now, in fact. Big question for me is, can we satisfy the simple but important exact constraint of exactness for all 1 electron densities without losing the 17 exact constraints that are already satisfied by R2 scan? That has turned out to be a difficult problem, and I've spent a lot of time working on that. And I'm always hopeful. I'm still hopeful now, but we haven't done it yet. And if we can do that, how far will this go toward a universally accurate but practical ground state density functional? Well, I can't answer that, so stay tuned for further developments. Don't expect them to come too fast because progress in DFT, progress in the approximations in particular, has been slow, but it's been steady over the years. Finally, I want to thank Allan for doing so much to advance condensed matter physics, starting in 1975 and up to the present day. So thank you.
Okay, so I think we have about 2 minutes for questions, and perhaps Professor Pickett could come up and start getting set up while we're doing that. Is there a question there?
So what's the implication of using this improved functional on the band gap problem of solids? Is it like a just better DFT eigenvalue gap obtained from this new functional? Is that the implication?
Okay, good question. I didn't mention the band gap, but we have looked at the band gaps. And the problem with the LSDA and the PBE is that they predict band gaps that are too small. You can see that as a problem or not. It's certainly a problem from a practical point of view. From a theoretical point of view, it's not a problem because we know that if you had the exact Cohen-Sham potential, if you had the exact Cohen-Sham functional and the exact Cohen-Sham potential, the band gaps would come out too small. And they would come out roughly like the the LSDA and PBE gaps and not like the experimental ones. And that's because the theory is a ground state theory. And even though you can think of the band gap as a difference of three ground state energies, if you compute it from the orbital energies, there's a missing contribution from the derivative discontinuity to the gap. So now your question is, what happens if we do R2 scan or scan? The gap opens up further, it improves, but not dramatically. Okay, so we're still underestimating the gaps. I think that with the self-interaction correction, if we can get it to work with R2 scan, because that will be implemented in a fully non-local generalized cone-sham approach, I think it will give correct gaps, but we're not there yet.
Okay, I think actually we should move on. Let's thank the speaker once again.